Okay, now we've looked at double integrals and practiced solving a few of those, setting up regions and integrating. What we want to do now is add on to that what we know about polar. So what we want to do is we want to look at taking a rectangular region and maybe if we have trouble integrating over that region, maybe we can change it to a polar region. I'll show you an example of that in a minute. But first of all, I want to show you how to go from rectangular regions to polar regions, or a double integral with rectangular coordinates to a double integral with polar. Now, first of all, I want to go back and just look at a circular sector. This is something we looked at before. And let's suppose that I've got just theta in here. And of course, I've got the radius. Here's radius. And I want to remind you of how do we get the area of a circular sector? So that's where we want to start. If we've got a circular sector, well, what we do is we say, well, I know how to get the area of a circle. It's pi r squared. And here, I've got a fraction of the circle. And the question is, well, what fraction of the circle is it? Is it a quarter circle or what? So what we do is we take theta, which is the angle that we have, and we say, okay, I know that there are 2 pi radians in a complete circle. So we take theta divided by 2 pi, and that gives us the fraction of the circle that we're dealing with. And our particular thing that we're looking at is area. So it's the fraction of pi r squared. We're saying, well, what fraction of the circle is that? And so these pi's divide out, and what you're left with is theta over 2 r squared. So if you give me the angle and the radius of the circle, I can give you the area of the sector of the circle that we're dealing with. Okay, so that's something we need to keep in mind. Now, we want to build on that a little bit and look at this situation here. Let's suppose that we've got a sector here, but we're going to do this. I'm going to say, I'm not going to go all the way back to the origin or the pole. I'm not going to go all the way back to where the radius is 0. I'm going to say I've got radius 1, and that radius 1 is this, and then then the overall radius 2, is this whole thing. Okay, so radius 2 would be this whole thing. And what I want to do, my objective, is to get this area right here. That's what I want. So it's not a complete sector. Well, and let's do this. Let's call this delta theta. Let's just say we start here with an angle, and then we rotate up, and let's say this is delta theta. So we'll call that angle in there delta theta. That's R2. It's supposed to be R2. Sorry about that. Okay, so here's R2. And of course, if you have a circle of radius R2, then the diameter is D2, and we call that an R2D2 circle. So, yeah, that's a little known fact. Now, so here we've got this R2D2 circle. And what I want to do is I want to get this sector right here. I want to get this area of this sector. So here's what I want to do. I want to take the full sector, which is delta theta over 2 R2 squared. That's the whole sector, right? That's the area of the whole sector. And I'm going to subtract off this part that I don't need. And this part right here is what I don't need. So it's getting subtracted off. So it's delta theta over 2 and R1 squared. Okay? Now, there's no question that that would be the area of that little sector that we're dealing with, that little partial sector. Now, here's what I want to do. I want to factor out a common factor. And it looks like a common factor here would be delta theta over 2. And what I have now is R2 squared minus R1 squared. There's what I have. Now, that looks an awful lot like a difference of squares. That's because that's what it is, right? So I can say, okay, I've got delta theta over 2. This is R2 minus R1 times R2 plus R1. See, so I'm just developing something algebraically here. Okay, does everybody see that? Now, look at this. Let me do some rearranging here. This is delta theta. That's what that is. R2 minus R1, well, that's, I'm going to call delta R, right? That's the change in R. It's the change in R from here to here, right? Okay, there's no question about that. That's that. And now you might be saying, hey, you left off the 2. You made another mistake. No, I didn't. I didn't leave it off. I haven't finished. Because now what I'm going to do is I'm going to say R2 plus R1 over 2. Now, look, I've got everything included. All I've done is some rearranging. Now, if you look at this right here, R2 plus R1 over 2, that's like the average, isn't it? That is the average. That's the average radius length. So maybe up here somewhere. So look, here's what we've got now. The area of this thing right here is going to be delta theta, delta R, and I'll just say R with a little bar over it, okay? The average radius. That's the area of that thing. Okay, any questions about that? Everybody see how that goes? Just straightforward algebra. Okay, now let's go to the next step. Let's suppose that, let me just complicate up the things a little bit here. Let's suppose that I break this thing down into little parts, sort of like we did when we talked about in Cal 1 when we broke things into rectangles under a curve, and then in double integrals when we broke things down into rectangular prisms under a surface. Now I'm breaking this thing down into this little region here. I'm breaking down into little circular things, right? These things. Okay. Now, let's suppose that I just keep R fixed. Theta fixed. In other words, I'm going from this right here to this right here. I've got maybe alpha and then beta. And then here is the delta theta. So I'm going from alpha to beta. And let's just suppose that I'm interested in all of this right here. I'm interested in adding up these things and getting the area. Well, let me keep theta fixed, okay? So theta fixed, and now let's look at this right here. Let's suppose I've just got theta fixed, and I go up here and I've got these R's in here, right? Okay. Now, if theta is fixed, let's think about the area of each one of these things, where I've put the little purple dot. First of all, this first one. Well, it's going to be, now remember, this right here, this is delta theta, right? Okay, this is delta theta. And I'm going to have delta R, right? Okay, because we have this and this. We have these two R's right here, right? There's delta R. Does everybody see what I'm doing now? Okay, so I'm looking at this, and here's delta R. And then I'm going to take this little R1 here, which is like the, it's like the average, right? Right? Remember we said this. We said delta theta, delta R, R average. So I'm just going to say this R1 is the, okay. Let me close that back. Sorry about that. Okay. So I'm just saying like this is R1 here, right? Now, does everybody see, okay, that's going to be the area of that thing approximately, right? Any questions about that? It's the average. If this is radius, if this right here is radius 2 and this is radius 1, It's the average between there. Okay? Any questions about that? Now, I could do this same thing. Now, notice, theta is fixed, right? And let's just go ahead and cut to the chase here. Theta is fixed, and it's going to go from alpha to beta, right? It's going to go from alpha to beta. Okay. Now, let's suppose that this is, I've already called that R1 and R2. Let me just call this R that corresponds to alpha. And, well, no, I can't do that. Let's just say this is R sub A, and this is R sub B. Okay? In other words, let's suppose that the radius, the smallest radius is R sub A, and the largest one is R sub B. Now, what is the radius going to go to? It's going to go R sub A, R sub B. Okay? Does everybody see that? So look, I keep, for every beta I keep fixed, for every theta, and theta goes from alpha to beta, R goes from R sub A to R sub B, right? It goes from here all the way to here. From here all the way to here, right? So you give me a theta. Here's a theta. I start here, and it goes all the way up to here, and I calculate all those in there, right? Any questions? Now, imagine that you have a diagonal across here. And just, so we've got this little sector here divided into little intervals. What if we let that little sector there go to 0? In other words, what we're doing is we're adding up all of these things, right? What if we continually increase the number of these little regions here, and such that the longest diagonal gets smaller and smaller and smaller because there's more and more of those things, right? If I do that, then we're playing the same game we've been playing with integrals, right? We're taking sums, a double sum, and we are letting the number of little subdivisions go to infinity, or in other words, the size of the largest one go to 0. And what we do is we get these integrals, right? Do y'all see that? Now, this is going to be R dr d theta. So we get an integral set up like this. Now, what this will do is this will give us the area of this little region here, this little circular region. Okay? This little part of a circle. Does everybody see that? Now, I didn't use summation notation or anything like we usually do, like with the double integrals, because I'm just kind of building on what we've already done. But you see that this would lead to the double integral. Any questions about that? Okay? Because that's what integrals do. They sum up in infinitely many things. Now, look, this is basically the point. Actually, you know, when we write the integral, we don't have the delta x. We have the d, right? Okay. R dr d theta is what it would be. Okay. I left out the summation, but I forgot, not to write the delta theta. But this is the type of integral that we're going to use to find areas like that. So now let's go to the next step. Let's suppose that I've got some interval down here, and I come up here and go over here, okay? And what I'm trying to do is, we don't always have circles, right? So let's suppose that we have this curve down here, and what we would do is, notice that I've got this little sector out here, and this is what I would divide up. That's what I would divide up. And actually, I would divide the whole thing up. And you see there's part of this that doesn't, it's too much, right? It's outside, because what we want is we want this all back here. And what I've got here is a little bit too much. See? So what we would do is we reduce the size of these little sectors, right? So that the error gets diminished, right? So our sum, when we're summing up all these little parts of this sector, and we let the number of parts go to infinity, we get this double integral, and it's going to be the exact value. Do y'all see that? Now, this is how we get area. What if we're trying to get the volume under a surface? Well, we've got this, but we've got this surface up here. Well, this is going to give us the area. To get the volume, we need to multiply by the height. Y'all see that? So what we would have that would be different is we would have this integral. We would have an integral over this region, and we would have f of r theta, r dr d theta. Okay? So we're given a function in terms of r and theta, or a surface that's described in terms of r and theta. We're trying to get the volume under that surface and this over this region. And this is a polar region. Okay, does everybody see that? Any questions? So instead of adding up all these right rectangular prisms, we're adding up these other things. They're kind of circular, right? Now, so let's look at this. Let's suppose that we have this region here. Let's suppose that we have f of xy equals, let's do this. Let's suppose we've got 25 minus x squared minus y squared. And what we want is we want the volume bounded by this above, and above by, let's say, the first octant. Okay? Now, I'm going to do this without polar at first. I'm going to set it up without polar and show you the power of polar here, or how polar helps to make your life easier. So here's what we've got. We've got z is equal to 25 minus x squared minus y squared, and we want to get the volume below that and above the xy plane in the first octant, let's say. Well, let me see what's going on the xy plane by letting z be 0. And when I do that, I get x squared plus y squared equals 25. And we learned in pre-K that that's a circle, right? Okay. Okay, so here's a circle. And let me draw a perfect circle there. There it is. Absolutely. Now, that circle is x squared plus y squared equals 25. Now I've got to say what x and y is doing. So let me do this. Set up my double integral. And by the way, this is 25 minus x squared minus y squared. And I've got to decide, do I integrate with respect to x or y first? I don't think it's going to matter much. I think what I'll do, though, is I think I will solve and get y equals the square root of 25 minus x squared. Okay? So I'll integrate with respect to y first. So I'm going to go from 0 to the square root of 25 minus y squared. So you give me an x. Here's an x. X squared. Let's see here. X squared. Okay. You give me an x, and I will integrate from 0 to the curve. Here's another x, 0 to the curve. See, no matter how you fix x, I'm going to go from 0 to 25 minus x squared. Now, the y part is easy because the y part is just simply going to go from 0 to 5. Right? Or the x part, I'm sorry, the x part. See, the x goes from here over to here. So 0 to 5. Now, you may be saying, okay, that was good. That was nice and easy, not too challenging. The challenging part of this one comes with the integration. Because now, let's take a minute and dig this. I've got 0, well, let me go ahead and integrate it. I might as well go ahead and give this a try. This is going to be 25y minus x squared y minus 1/3 y cubed. And that's going from 0 to the square root of 25 minus x squared. dx. Okay? So it's not too bad. Now, it's starting to look a little bit ugly, though. I got to be honest. And now we've got 0 to 5. Now let's put everything in. 25 times 25 minus x squared, 25 minus x squared, minus 1/3, 25 minus x squared to the 3/2 dx. Now, that integral kind of looks like a handful, doesn't it? That integral's got some meat on its bones. It's intimidating. So I'm thinking, I wish there was some other coordinate system that I could use. I would just wish there was something. Well, maybe there is. Maybe there is. Because let's look in an alternative way. Let's look at this thing. We've got z is equal to 25 minus x squared minus y squared. Isn't that 25 minus r squared? Because x squared plus y squared is r squared. Recall that from your polar, right? X squared plus y squared equals r squared. Isn't that true? So 25 minus x squared minus y squared is equal to 25 minus x squared plus y squared. And that's 25 minus r squared. So that's a little bit easier. Now, so let's see what we've got here. So what we've got now is we've got, instead of that other thing in here, we've got 25 minus r squared. Now, let's see what we have down on the xy plane. Instead of x squared plus y squared equals 25, we've got r equals 5, right? R equals 5. Okay, so let me just draw that. Here, r equals 5. Now, what does theta do down here? If we're dealing with the first octant, what is the smallest value for theta and the largest value? 0 to pi over 2. And what does r do? No matter how I fix theta, r goes from 0 to 5, right? Ah, look at this. That's a lot easier. Now, I'm not finished because every time I integrate in polar, I've got to do this right here, r dr d theta. It's got to have the r dr on it, always. Right? Because remember, that was part of the formula. When we're getting those little sectors, the area of those sectors were involved r dr. Like you're laughing, r dr, r dr. Okay? Now, okay, does everybody see this? Now, I don't know about you, but I would rather integrate that than that other thing. That other thing was a beast, right? This thing is manageable. This thing is not intimidating to anybody. Well, so let's see. Let me simplify it a little bit. This is going to be 25r minus r cubed dr d theta, right? And that's an integral that no matter who you are, you would find that simple. Okay. So let's go ahead and tackle it. We've got 0 to pi over 2. This is going to be 25 halves r squared minus 1/4 r to the 4th. And we're going from 0 to 5. And then d theta, of course. Okay? Now, I've just got to put in the 5, and I don't even need to put in the 0, because now here, notice what we have. We've got 0 to pi over 2, and this is going to give us 25 times 25, so let's do 25 halves times 25 right there. And I won't, now 1/4, what's 5 to the 4th? 625. Okay, so 625 d theta. Okay. So what is this? Is this 625 as well? 25 times 25? Okay. 6 25 over 2 minus 1/4, 625 d theta. Now, I guess we have a common denominator there. Why don't I just factor out the 1/4? Would that do it? Let me factor out the 1/4, and that might be a way that we can proceed with this integration a little more easily. 2 times 625, is that 1250? Right? So this is going to be 1250, isn't it? If I factor out the 1/4, then I would be multiplying this by 4, right? Do y'all see that? Okay, I think that has it. And then minus 625. I realize there are simpler ways to do this. I mean, you've got 625 halves minus 1/4 half, but I'm just going through, just showing you how you can simplify if you don't recognize any kind of shortcuts, arithmetic shortcuts. I factored that out. So what do I have now? I have 1/4, 0 to pi over 2, and 1250 minus 620. Is that 625? Okay. So now we have this. We have 625 over 4 theta, and theta goes from 0 to pi over 2. So our answer is going to be 625 over 4 times pi over 2. And that's going to be the volume, right? I mean, we could subtract off the 0. No point in that, right? Does 4 don't go into 625, does it? So we're pretty much, huh? Okay, any questions about that?